guy right here. Well, first, what does it mean if I ask you to find a solution? What is a solution? What would define a solution? How would you know you had a solution? Don't be shy. For a while, because I cannot wait to do that waiting. What's the solution, and how would you know you had a solution?
So there are functions.
What are functions?
Those are functions.
These are functions, yes. These are functions. They're represented as equations. Yeah. What's that?
They have inputs and outputs.
They have inputs and outputs. That's important.
The output would be the solution.
What's that?
The output would be the solution.
The output would be the solution. The solution, a solution, is an input and an output. Right? They go together in such a way that way. You know, we have a solution, an input, and an output. Get what? Maybe you're having trouble verbalizing it. What is an example of a solution for this equation, for this function? Okay, give me a solution.
First one?
For the first one.
0, 0.
0, 0. 0, 0. Is that a solution? How do you know it is?
Because when you plug the 2 points in, it evens it out. Like
Yep.
each side is equal.
Exactly. If I put this in for x and this in for y, it's true. It is equal. Okay, another one? 1, 1. 1 goes in, 1 squared, 1 comes out. Another one?
2, 4.
2, 4. What if we let x be negative? What if we go to the negative?
-1 and 1.
-1 and still +1. Why is that? Why didn't it come out negative?
If you do -1 squared, it's -1 times -1, and that's positive.
So do you think, are we gonna get any outputs that are negative from x squared? No, you square a number, it's either positive times positive or negative times negative, and either way, that's positive. Okay, is that the negative x?
-2
-2,
and 1
and what?
is positive 4.
+4, -2 times -2 is +4. Okay, and we'll stay with that. We'll stay with those 5. Those are good 5. If you're not sure what a function is like, or what it does, maybe what its graph looks like, that kind of thing, just plug it in numbers for x and getting numbers out for y is a good place to start. Okay, and it is for us as mathematicians. Okay, it is a beginning. It is a good place to start. It's not where we want to be forever. Okay? We don't want to be guessing checkers forever, and we don't want to be plugging chuggers forever. Okay? We want, as mathematicians, to be able to manipulate equations and be able to recognize patterns and utilize those patterns, and manipulate those patterns. Okay? So that's what we're going to be working on today. We're going to be looking at graphs of these functions and utilizing, taking advantage of those patterns that we recognize arising. Right? So look at a few patterns in these examples, and then try and use our inductive reasoning to extrapolate it out to all situations like these situations. Well, first we get an idea of how the x squared function acts. Okay, for one thing, it always puts out positive numbers. We talked about that. If we were to go from 0 to 1 to 2, we see we go from 0 to 1 to 4. If we went to 3 as our input, what would be our output? 9. What would be the one after that? If we put in 4. And then after that? 25. After that?
26.
After that?
49.
After that? After that? And after that? Okay. Well, This is different than, say, like y equals x, right? Y equals x was just, it goes 1, out comes 1. It goes 2, out comes 2. It goes 3, out comes 3. Right? Even like 5x. It goes 1, out comes 5, 2, comma 10, 3, comma 15, right? In this predictable, like, linear way. You're just stepping up. For every amount that you move over, you move up the same amount, right? Move over 1, move up 5. Over 1, up 5. Over 1, up 5. Is that the way this works? Move over 1, move up 1. Move over another 1, move up 3. Move up another 1 if we went to 3. Move up 5. Move up another 1, go up 7, right? So there's not this like up and over behavior. If we were to graph it, we get 1, comma 1, 2, comma 4, 3, comma 5, 6, 7, 8, 9. 9, like that. Right? And where our lines would drop down into the third quadrant, right, going down into here. This one, like we said, it only gives out positive numbers. And the negative numbers get the exact same outputs as the positive ones do. Right? Negative 2 puts out the same thing as positive 2 does. Negative 2 squared is 4, and so is positive 2 squared is 4. Right? So negative 1, comma 1, negative 2, comma 4, negative 3, comma positive 9. So now we just start to notice other things about this graph. What's a word you would use to describe the nature of this graph? Fancy math word. Curved. It's curved. It is a curve. Most graphs are curves, and actually we qualify lines as curves in math at least. There's a reflection about it. Is there a reflection about all graphs? Are all graphs, they all have reflections? No, this one does, right? You can put a mirror down and reflect the right side on the left side, and it would produce the exact same thing. What do we call that quality in math? Don't call it a reflection. If it's a reflection onto itself, if it's exactly the same on one side as it is on the other, starts with S. What?
Similar?
No, not similar. Similar would be comparing two things.
Symmetrical.
Symmetrical, yeah, we're symmetrical. Our faces are symmetrical, our entire bodies are symmetrical. Lots of things are symmetrical, right? Out there.
Look outside for an example.
Like if you look at a lot of things are symmetrical. You look at the front of a car. The front of a car typically is symmetrical, right? Even the logos a lot of times are symmetrical. One headlight on the right, one headlight on the left. It's all symmetrical and nice. You get in the car, it's not exactly symmetrical, right? There's a steering wheel on one side and not on the other. Okay, that would cause a lot of problems. If you go into, this is something that I've noticed, and probably you've noticed as well. If you walk into a building and say you're a guy, you're looking for the men's room, but you can't find the men's room, but you do find the women's room, how do you kind of use your logical reasoning to find the men's room?
The other side.
The other side of something, right? You have a water fountain or a door or a staircase or something. Usually they set those things up symmetrically, right? Guys room here, girls room here. If it's not like that, it can be a little confusing. But typically that's what our minds look for. Like, oh, there's that there. There's a plant and there's a staircase. There's another plant. Probably the guy's room is over there, right? Symmetry. We like things to be symmetrical. So now that we've noticed it's symmetrical, we've noticed that if we just had y equals x squared, we'd never get a negative number out of there, because when we square numbers, we always get positive numbers. Let's move on to this red guy right here and see how it's different, how its outputs are different, how its graph is different. Okay, the first thing that I want you to see, and again, I want you to notice patterns with me. I don't want you to stay in the rut of plugging numbers in and getting numbers out, and that's the only way I can plot a graph, okay? I want you to come with me and notice these patterns and utilize them. The first thing that I want you to notice is that all of these functions we can think of as like starting with x squared. Right? Here's x squared, add 3, right? Whatever comes out of here, add 3 to it. Whatever comes out of here, multiply it by 4. Whatever comes out of here, multiply it by -1. See what I'm saying? Okay. Think of it this way. Something goes in, right? Talking about our factories here. Something goes in and gets squared. Okay? So this function does exactly what this function does. They do the exact same thing, at least at some stage. So this number also squares numbers. It just takes a number and squares it. But then it does something more when it gets done with that, right? When it gets done squaring something, it takes that output and adds 3 to it. So think about what that would do to the output. Right? Think about what that would do to the graph. And the graph is just input and output as well. It's the exact same thing as writing 0, 0, only instead of writing the number 0 and the number 0, we write a dot at 0 and 0. Okay. So let's look at how it changes. 0 goes in, it gets squared, right? So far we've done the same thing. Just square 0. But here, after we square 0, we add 3, and we get 3. Here, we go in here, we square 1. Well, rather than doing this work over and over again, we could just look at these outputs, right? It's going to take a number and square it. It's going to do the exact same thing as this guy. And then it's just going to add 3. So we could just take this and we could add 3. We could take this and we could add 3. We get 4. We could add 3. We get 7, add 3. Again, and get 4, and add 3, and again, get 7. Okay. Remember how we said we go over 1, and we go up 1. We go over another one, we go up 3. Right? So we go over 1, right, and we go up 1. We go over another one, we go up 3. Right? We still have that same kind of behavior. It's just that these numbers are 3 bigger than these numbers. Y'all good with that? Making sense? Okay. So all of these outputs are the same as these ones. They're just 3 bigger. Right? 3 bigger than these ones. Let's look at the graph. How's the graph look different? Okay. As numbers, these numbers are 3 bigger. Right? The outputs are 3 bigger. Where do we put outputs on a graph? The y, right? And the y which runs which direction? Vertical, okay? Right? The outputs are 3 bigger. How do we show bigger numbers in the vertical? Higher up, right? Up, not down, up. Okay? So instead of going through 0, 0, we go through, right? Not 0, 0, but up 3, 0, 3. Right? Not 1, 1, but up 3 from there. 1, 2, 3. 1, 4. Okay? Not 2, 4. Let's see. 4. But up 4 from there. 1, 2, or up 3 from there, sorry. Up 3 from there at 7. It has the exact same shape, symmetry, steepness, and all these things are the same. It just has moved up 3. Well, what if we replace this 3 with a 7? How would that change? How would that change the graph? Be steeper? Be higher up, right? It would just be up here, whereas this guy's down here. This one, if we added 7, would be, you know, it wouldn't start at 0, 0, start at 0, 7. Remember that, I think it says right there, 0, 7. Okay. What if we subtracted 8? How would that do? We can go down 8. Okay. So our inductive reasoning tells us that if I take x squared, right, I'm just squaring a number, I'm just getting these outputs, and then I add a number to it, or I subtract a number from it, the graph moves up or moves down, depending on how I use it. If I add 3 to all the outputs, since output is vertical on a graph, they move up. Or if I subtract, they move down. Okay. Next one. Again, I want you to think, this does the exact same thing as this first function, only a little more. It takes x squared, does a little more to it. First it takes x squared, it takes x and squares it, and then whatever happens there, whatever you get when you square x, you're going to multiply that by 4. And then there's your new output, right? That's the output we get in this column. 0 goes in, gets squared. 0 squared is 0 times 4 is 0. Different from this one, not 3, because we didn't add 3. Like, we didn't allow that change from 0. It's still just multiplying, and so we still just have 0. 1 goes in, 1 gets squared and becomes 1, just like this did. Then we multiply that by 4. Multiply that by 4, and you get 4. 2 goes in, when you square it, you get 4. After you're done squaring it, what do you do with it? Multiply it by 4. Multiply it by 4, you get 16. Negative 1 goes in, when you square it, you get 1. Then when you multiply it by 4, you get 4. When negative 2 goes in, you square it, you get 4. You multiply that by 4, you get 16. So x goes up by 1, y goes up by 1. X goes up by another 1, y goes up by a 3, right? If x were to go up by another 1, 3, y would be 9, that would be up another 5. This one, when x goes up 1, y goes up 3, right? Just to start, or up 4 just to start with, where this just went up 1. You go up another 1, and it jumps another 12, right? Instead of another 3, it jumps another 12. Okay? So this doesn't seem to be just a simple shift, right? It's changed this over and up behavior. When you go over, you go up even more than you did for x squared. If we looked at the graph, 0, 0 still. 1, comma, 1, 2, 3, 4. 2, comma, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And we connect those points. So how is multiplying by 4 change the graph?
Makes this narrower.
Well, okay. I'm going to go with steeper. I'm going to prefer steeper over narrower. Okay. The reason why is, if you take this and you say it goes narrower, a lot of times in my experience, my own experience included as a student, there's a feeling that, like, when this shape goes narrower, that, like, you don't put in the same values of x. Like, that shape just gets moved in like that. And I guess there's some truth in that, but there is definitely some confusion that has gone along with that as well. If we say steeper, though, it's going to like go through all the same values. It's going to accept all the same x values. It's going to output the same y values. It's just going to do it faster. So, and if we say steeper, that idea carries through all the way through calculus, right? That a graph is steeper. So those are my reasons. Not that narrower is bad. Just steeper is, it carries through for longer. All right, so it made it steeper. Multiplying by 4 made it steeper. What if I multiply by 6? Make it steeper? Even steeper than that? What if I multiply by 2? Steeper than that. Not as steep as multiplying by 4. Can we make it less steep than this? Negative. Maybe negative.
I'm not sure it's flip it.
Would that flip it? Okay, so that's an idea too, right? If we multiply by negatives, then we're going to make positives into negatives. Okay. So that might be true. So maybe negatives, or maybe negatives just flip it. If that's true, if negatives just flip it, then what would make it less steep if it's not negatives? 0? Well, if you did 0 times x squared, then you just always get 0. You get a flat line at 0. What can make it less steep? This makes it 4 times as steep. What would make it half as steep? Fraction, like 1/2. Multiply by a half. Multiply by a fourth, you get this fourth as steep. 3/4. 3/4 as steep. Okay. Because remember what I'm saying here. The output of this function is the same until you multiply it by 4. But just before that, it was still just x squared. It had the same output as this function. So it was 1 until we multiply it by 4. Now it takes it all the way up from 1 to 4. Right? It takes that output and multiplies it by whatever. Multiplies it by 4. If we multiply by half that output of 1, this output of 1, if we multiply that output of 1 by 1/2, 1 times 1/2 is 1/2. Okay. 4, right, 2, 4. 4 times 1/2 would be just 2. So everything would be cut down in half. So this number guy, this guy right here, this number, affects the steepness. 4 is steeper, 2 is steeper, 3 is steeper. 1 is the same steepness, right? Haven't changed anything, we multiply by 1. 1/2 is half as steep. 1/3 is 1/3 as steep. Alright? This last guy, same thing. It has the same output as that blue function until you take the x squared and you multiply it by a -1. Make that output negative. So up here at the stage, just at the x squared part of it, it's all the same. You're still going to get 0, 0, 1, 1, 2, 4, -1, 1, -2, 4. But they're going to take that x squared, these are all x squareds, and you're going to multiply it by a negative. You're going to get 0, that's x squared, right, that's x squared. We're going to multiply it by a negative, 0 times negative is still 0. But 1 times -1, 1 times -1 is -1, 4 times -1 is -4, 1 times -1 again, -1, and we get -4, 4 times -1 is -4. Well, see here, we have 0, 0, 1, 1, 2, 4, 3, 9. Come over here, it's 0, 0, 1, -1, 2, -4, -1, -1, -2, -4. It's all the same except for it's exactly the opposite. So this graph's going to look exactly the same, only instead of going up to positive values, you can go down to negative values. Down to negative values. 0, 0, 1, -1, 2, -4, 3, -9. And same for negative values. -1, -1, -2, -4, -3, -9. Right, so if we use y equals x squared as the standard, what changes have we made that graph go through to make the other graphs? What's one thing that we've done to the graph? What's one thing that makes these graphs different? What's that? Well, actually to x, you're still squaring x. It's what you do to after that. But like, how is this graph different from this graph? It's higher up, right? The graph itself, the graph is a picture. Okay, so pictures are big, and they're up and they're down and the left and the right, and they're right side up and upside down. Right. Outputs have 3 added to them. Graphs move up and down. Right? Move right and left. So we can move them up. What else?
Steeper.
Make them steeper or less steep. And what else have we done? We made them flip upside down. That's what we've done so far. We'll do other things, but that's what we've been able to do so far. That letter seems a little strange to use, but it's just how it is. It's how it is for now. Right. So what is adding something on after you square? What does that do to the graph? Up and down. How about if we multiply it by a? That changes what?
Left or right?
Multiply by a moves it left or right? Makes it steeper? Steeper? How about just the steepness? It might be less steep, might be more steep. More steep if it's bigger than 1, less steep if it's this fraction. And then if we multiply by a negative, if that number up front happens to be negative, it has the added effect of what? Right. What's that? Moves left to right? Let's see, we multiplied by a negative. Here we multiply by a negative. Would you say move it left and right? Move it to the right. Here's the original graph, and here's the graph after you multiply every output by a negative.
Moves it down.
Flips it over, right? It takes this output of 1 and makes it negative, negative 1. Takes this output of 4, makes it negative, now it's a negative 4. Right? I've moved my x-axis up here so that we have room down below to graph it. Takes the output of 9, makes it negative 9. Because right here, that's going to give the same exact outputs as x squared. But then we multiply it by a negative. This one's going to have the same exact output as x squared, then you multiply it by 4. This is going to have the same exact output as x squared, then you're going to add 3 to that output. So that negative flips it vertically. Okay, so I'm going to give you one to graph. It's in 4.1, and I want you to, like I said, utilize these patterns that we're recognizing. If you plug in x's and find out y's, then it's not worthless work, right? It still is doing something. It's still encouraging a truth about the graph, that if you plug in an x and you get out a y, when you graph it, and you put in that x and that y, that xy point on the graph represents an x and a y that satisfies the equation, makes the equation true. But if you want to move on, if you want to stretch your brain a little bit, then work with these patterns as well. Okay. It's best if this explanation, if it didn't quite grab you, you didn't quite understand it, it would be a good idea to go back and watch this video, or look at the PDF or whatever, or sit down with some examples, working them out yourself and see, I see, that's why it moves up 3. Now that's why it makes it steeper. That's why it flips it upside down, right? So for now, what I'm going to give you is just something to practice on 4.1. And this is 33. 33 has different instructions, but I want you to go ahead and just graph it. Just graph that one for 33. And when you graph 33, then it'll be easier to answer the question with that. This has all the elements that we've been talking about. What is this going to cause to happen? Flip it upside down, so upside down. And this guy is 6, multiplying by 6, taking that output of x squared and multiplying it by 6, making it 6 times steeper, making the output 6 times bigger, making every step of x, every move over like 1 for x, 6 times as big as just squaring it. We square it and then we multiply it by 6, making it 6 times bigger, 6 times steeper. Okay. Then we take all that, put it all together, we flipped it over, we made it 6 times steeper, okay, and then we subtract 1. What's that going to do?
Move it down 1.
Gonna move it down 1. So we can take, let's see, this is 0, 0. This is for y equals x squared. 0, 1, 1, 2, 4, negative 1, 1, negative 2, 4. Just take that, take some of those points, and flip and make it steeper and move it down and all that kind of stuff. We come up with this graph over here. we can do it in stages. We can do it all at once. We can do a couple at once and then do another one after that. Like, we can take this, make it 6 times steeper, right? So instead of 1, 1, it's 1, 6. It's 4, 5, 6. And instead of 2, 4, it's 2, 24, right? 6 times steeper. Move that up there. So 1, instead of 1, 1, and even instead of 1, 6, it's going to be down negative, right? Because it's not just a 6, it's a negative 6. So 1, 2, 3, 4, 5, 6. 1, negative 6. So now we've flipped it upside down and we've made it 6 times steeper, but we haven't moved it down 1. We haven't subtracted 1 from it yet. 2 and negative, what's it, 6? Negative 24. It's a lot steeper, 6 times steeper. 0, 0 still. Again, we haven't moved it down 1. We've only multiplied it by negative 6. Symmetry helps us. Just reflect those over the line of symmetry. Okay. And then, last thing, everything gets moved down 1. So move this down 1, this down 1, this one, and this one, and this one. To negative 25. Okay, so we go through all these blue points. The steeper it is, probably the harder it is to graph. We get right through those points. We made it steeper. It's opening down now instead of opening up, and we moved it down 1. We shifted all of those points down 1. Every one of those points. Let's do something more. Let's do a different kind of change. Now we've got moving it up and down, we've got changing the steepness, and we've got flipping it upside down. We have those two. What's going to cause it to be flipped upside down? Where? In front of the x squared. And then moving it up, what are we going to do to move it up?
A variable after the x.
Add a constant, right? Yeah. A number, yeah. So we add a number after the x squared, we're moving it up. All right, so let's see what this would be. I equals x minus 3 squared. So we're still squaring numbers. This is the name of the game in this kind of a function. They're called quadratic functions. When we take a number and square it, right? We don't just take it and multiply it by 5, but we square it first, and then we multiply 5 or whatever, but we square it. Right? That's called a quadratic. When you have x squared in your equation, and x squared is the biggest power of x, then that's it. That's a quadratic equation, or quadratic function. Okay? So go ahead and put this quadratic equation. I want you to make a guess as to what that minus 3 is going to do. We're still squaring numbers, but we're subtracting 3 from them first. See if you can think of what might happen to the graph, and then graph it and see what happens if you're. All the stuff we're doing with graphs, shifting them and making them steeper and all that kind of stuff. Is this sounding familiar to something we've done before? So, does it? Is it familiar? Have we done this before? We shifted the graph up and down, left and right, made it steeper and less steep. An answer would be good. Any answer, yes or no, would be good. Yeah? What do we do it with? What kind of a function? Huh? Yeah, we do it at absolute values. We shifted them up, and we shifted them down, we shifted them right and left, and made them steeper and flipped them upside down. It's all the same thing. And if you're paying attention and you're allowing yourself to learn new things and stretch your brain a little bit to beyond what it might know right now, it becomes pretty simple. Like, we're going to do this with lots of functions. With the absolute value function, with exponential functions and logarithmic functions, quadratic functions, cubic functions, like all the functions. We take them and we put them through these shifts and these changes of steepness and flipping them upside down, it's all the same. Everything is repeated over again and we get to a new function. So if you can view this as, oh, I see, this parent function, this basic function x squared, when I take the outputs and I multiply them by 3, I get that. That makes the outputs 3 times bigger and therefore makes the graph 3 times as steep. If I add 1 to every output by putting plus 1 after x squared, I see why that would translate to the graph moving up 1. Then when it comes along to a new function, you're going to say, well, when I take the basic function that you talked about at the beginning, and I add 1, it's going to move it up 1. If I multiply it by 3, it's going to make it 3 times as steep. It's all the same. They all do the same things. And if we can recognize these patterns, this makes it all that much more easy to do. So maybe from our experience with absolute value functions, do you remember what would happen if we put a minus 3 in the absolute value with the x? Moves it left or right. Which way would it be if you subtract 3? It would move it right or it would move it left?
Right.
It would move it right. You're correct. Okay? I'm going to try to explain it a different way. It's going to be really similar to the absolute value thing, but try and help you understand why there's this shift to the right by 3. Why do all our x values go get bigger by 3? We'll start plugging in some x values, seeing what we would get from x squared, and seeing why it's different, and the way that it's different when we do x minus 3. Start with -2, -1, -3, no, -2, -1, 0. That's not going to go. 0, 1, 2, and 3. Right. So when I plug -2 into this function, I just square it. I just square -2 and I get 4. Okay? Into this function right here. When I plug in -1, I just square it and I get 1. 0 squared is 0. 1 squared, 2 squared, 3 squared. Take a look at this function. We're not changing the outputs, right? We're not taking something and squaring it and then doing something to it. We're still just squaring numbers. So this function does the same thing as this function. It takes a number and it squares it. Just the only difference is when you put a number in, you change it first and then you square it. But we should be able to get the same outputs. We should be able to get 4 and then 1, 0, 1, 4, 9. We should be able to square. Inside here we should be able to square -2 and square -1 and square 0, okay? But in order to square, say, -2, we'd have to start with a different x value. You can't just plug in -2 and it squares -2. Because if we put in -2 here, -2 minus 3 is -5, and when we take -5 and square it, we get 25. You take -1 in there, it doesn't square -1, it squares 3 less than that. Right? So it's like putting us 3 steps behind of this function. Does that make sense a little bit? This -3 is putting us 3 steps behind. Okay? So to make up for it, we have to, we'll see in a couple more. So we put -1, -1 minus 3 is -4, we square -4, we get 16. Right? 0, you put in 0, 0 minus 3 is -3, you square that, you get 9. Okay? But here's where we start to catch up. You get to 1. Now 1 is 3 bigger than -2, right? Where the normal function, you put in -2, you get out 4. In this function, you put in 1, you subtract 3, and only then do you get -2. 1 minus 3 is finally -2, right? So if we were to have started at -2, we have to, in this function, go all the way to 1 before what gets squared is -2. 1 minus 3 is -2. You square that, and you get 4. And now we're going to pick up the outputs where this one did. At -2 it had 4. Here at 1 we have 4. Right? At 1 we have the answer for -2 of the original function. And then at 2 we subtract 3. 2 minus 3 is -1. Right? Oh, -1. And when we square -1, we get 1. So we're getting 4, then 1. When we put in 3, 3 minus 3 is 0. When you square 0, you get 0. You get 4, you get 1, you get 0. If we went on to 4, we get an output of 1, 5 would give us 4, 6 would give us 9, and so on. Right? It has that same pattern, but we have to start out at 3 greater than just the x squared function. Right? This guy puts us 3 steps behind, so we have to come up 3 steps. We have to move over 3 steps. We have to move to the right 3 steps in order to get the same shape. So where this was at 0, 0, we have to go over to 3 in order to get an output of 0. Because before it ever gets squared, it gets 3 subtracted from it. And 2, 4, and 4, 4. Therefore we didn't go 4. If we did go 4, we would get our 4, let's see, 3, 0. Oh, sorry. Hold on. 2, 1. 1, 4. 4, 1. 5, 4. In order to find our center again, in order to find the same shape, we'd have to go over to the right 3. Because we're subtracting 3 from those things before we square them. So trying to help you to see, maybe through a different discussion, why when you subtract 3 does the graph move over 3. So now we've added one more thing in there. We can have a times now x minus, we'll call it h, plus k. How does k affect the graph?
Moves it up and down.
Moves it up and down. Negative affects it by
Flipping it vertically.
a.
Doesn't it flip vertically?
Negative
Or
does.
doesn't it?
But if we just think about the a part,
Is the steepness?
it affects the steepness. And now we've brought in this minus h. What does that affect the graph? On the graph.
Moving it left and right.
Left and right. Okay. And if we take, for example, y equals x plus 2 squared minus 3. Okay. So this minus 3 is going to do what to the graph?
To the right.
To the right, 3.
It's minus 3 after we square it, then we subtract 3 from the output.
Down.
Move it down 3. When we add 2 before we square anything, that's going to do what to the graph? To the left 2. Okay. Well, there's this real helpful point on the graph, and it's this point right here. Okay. This point has the same name as a similar point on the absolute value graph. Any idea what that might be called? Starts with a V. A V. Vertex. V is in vertex. Yeah. This guy right here, at the very bottom, if it opens up, at the very bottom, is called the vertex. Or, if it opens down, the very top would be the vertex. So, if the graph moves to the left 2 and down 3, well, all the points on the graph are going to move to the left 2 and down 3, including the vertex. And typically the vertex, it will start at 0, 0. And if it moves to the left 2, then it must, instead of being at x is 0, it's at x is negative 2. And if it moves down 3, then instead of y is 0, it's at y is negative 3. So there's our vertex. Our vertex at negative 2, negative 3. And if it's written like this, I think it's the most convenient form. It's called the vertex form. Vertex form to me is the most straightforward. It tells you move to the left, move to the right, move up, down. Here's the steepness, okay? Here's whether you should open up or open down. Should it be right side up? Should it be upside down? All that is here. Moves left, right, up, down. Affects the steepness. It's more steep or it's less steep. And this guy will flip it upside down. If it's negative. If it's not negative, then it's right side up. Vertex form is nice because you can find the vertex. y equals 2 times x plus 3 squared minus 1. It's going to move left 3 and down 1. So the vertex is at left 3 and down 1. 3, negative 1. And so, like, those two things are done. The moving left and right are done. The moving up and down are done. And now it's twice as steep. Okay? So instead of over 1 and up 1, it's over 1 and up 2. Instead of over 2 and up 4, it's over 2 and up 8. There's that symmetry right there, so we can reflect those points over the line of symmetry. And on our points, connect the points we've already plotted. So in 4.2, I'm going to give you number 7. Convenient, it's in Vertex Form, all that information is right there. Transfer that information from the equation onto the graph just by shifting it over, shifting it up, down. Subtract 2, I just went to the graph. Subtract 2 inside there with x. Huh?
I'm gonna move from left to right.
Moves it left to right, which?
Move to the right.
To the right. To the right is amount of 2. So, right 2, this one.
Moves it up.
Moves it up 4. This guy right here.
Makes it steeper.
Steeper, 4 times as steep. And since I circled the negative as well, it does what? Flips it over, flips it vertically. Okay. So that tells us the vertex is at 2, 4. It moves to the right 2. Vertex moves to the right 2 and up 4. There's our vertex right there. And if this was a regular, just if that's all that happened, and the steepness wasn't affected, then it would go like this, over 1 and down 1, and we go over 2 and down 4, over 2 from there and down 4. It would be like that. But our new graph is 4 times as steep as that, so instead of over 1 and down 1, it'd be over 1 and down 4, instead of over 2 and down. Over 2 and down 4 will be over 2 and down 16. There. And again, over 1 and down 4, over 2 and down 16. It should be a curve, not a point. Oh, we've incorporated all those changes. So vertex form, we find the vertex, we graph the vertex, that's left and right shift, up and down shift, that's both of those things all tied up in that one thing right there. And then from there, we just need to make sure that it opens up or down, whatever it should be doing, and if it's as steep as it should be. So, the thing though is, they won't always give you an equation in vertex form. I bring that up because I think the vertex form is the most convenient form. Just like mx plus b, right? Slope intercept form is probably the easiest way to see the equation of a line rather than ax plus by equals c. It's a little easier to see y equals mx plus b. A simpler. But it's not always going to be that way. It's not going to be in the most convenient form, and so let's look at other forms that the equation of a parabola can be in. A quadratic equation can be in several different forms. So one of them is vertex. If we take something like 28, y equals f of x equals x plus 5 squared minus 2. If I say 2 squared, what does that mean, 2 squared? By itself. I multiply by itself. Or 4 squared. It means multiply 4 by itself. So what does x plus 5 squared mean?
X plus 5 times x.
Exactly. X plus 5 times x plus 5. X plus 5 times itself. Just like anything else that's being squared, you multiply it by itself. So this can be rewritten as x plus 5 times x plus 5 minus 2. How do we multiply x plus 5 times x plus 5? Yes? Who said distributive? That's exactly what it is. Okay? Distributive. I love that answer because the answer that works okay and has worked okay for a while, but ultimately I don't like as much is foil. Right? You foil it. Have you heard foil before? I'm sure you have. You've heard foil before. Okay? Well, not to say the person who taught you foil was bad or they had, ill intentions or anything like that. But we're going to go beyond that. We're going to go beyond the limitations of foil. Foil has its limitations, and we're going to break through those this year. And so distributive property is perfect. Okay? And that's all foil is trying to get you to remember, is distributive property. To distribute everything from one parentheses into the other parentheses. Okay?
Please excuse the interruption. Please release the C squad volleyball players. Please release the C squad volleyball players. Thank you.
Brandon? That's
Yeah, I'm Brandon.
What's the green is on
I
the
would have thought you could be
You ready? Want to go?
on like maybe B squad.
No, I'm not the athlete in volleyball, but I am in football.
Oh, okay.
It's too bad.
If it doesn't work to just run through the net and knock people over.
It'd be really weird to see Keenan and scan it. I mean, not that it wouldn't be nice, but.
That's a lot of humor.
All right. Okay. So again, foil tries to help us remember that we're supposed to distribute everything to everything else. But if we can remember that ourselves, find a way to manage that also carries through every other possible situation, then that's better. It's stronger. Okay. So I'll remind you about foil. Foil tells us first, outside, inside, last, right? Multiply the firsts together, the outsides together, the insides together, and the lasts together, okay? Now what I'm gonna have you do, it will actually even take you through the exact same steps, although we don't have to do this in that order. We could do Leof, or Oilf, or it doesn't matter, because multiplication and addition are commutative and associative, and so it doesn't matter which order we do it in. Right? It would all come out the same. The thing that I want you to do instead, and I'll show you why afterwards, is just to remember, distribute everything that's in here to everything that's in here. Right? And here's one reason why. If I gave you x plus 5 times x squared plus 2x minus 3, then FOIL doesn't work anymore. It does not get everything. If we just followed FOIL, we would do firsts, insides, outsides, no. Hold on a second. Firsts, this is first. Firsts, let's see, first outsides, right? Insides and lasts. Notice nothing was ever multiplied by 2x if we just follow FOIL. Okay, FOIL's a mnemonic device. It helps us out for the level of difficulty that we were having in Algebra 1 to multiply two things together like this. But in Algebra 2 and beyond, we're going to be multiplying bigger polynomials together. That's what these are called. And FOIL just doesn't do it all. Okay? If instead we think everything in here has to get multiplied by everything in here. Now we just start with the first thing. We multiply it by everything in here. We distribute it just like we distribute like a 5 or a negative 2. We distribute the x to the x squared, then to the 2x, then to the negative 3, and then there's nothing else. So we're done. Then you distribute the 5, right? We're done with the x, and we move on to the 5. Distribute the 5, there, and that's it. Right? We distributed the 5 to everything, and there's nothing left to distribute, and so you're done. Everything's been distributed. Okay? And if we were to, let's see, let's take something like x plus 2 times x minus 3. Okay? This is all I'm showing you is multiplying two parentheses with two terms each in them. You can represent x like this. Let's say x is this long, okay? And here's a 1 and another 1, so that's 2. So this is x, and this is 2, so that's x plus 2. If we multiply by x minus 3, we can represent it as an area. Here's x, here's a 3. Let's do x plus 3, just to make things easier on ourselves, plus another 3. Okay, so this much is 3, this is x, so this side is x plus 3. So if we drew this as a rectangle, then this would be x plus 2 times x plus 3. It's like the area of a rectangle is just length times width. Well, that's this first part is x by x, or x times x, or x squared. This guy right here, should have made it a lot longer or a lot shorter. That'll be all right. This length is 2, this length is x, so this is 2 times x. This length is 3 and this length is x, so this guy is 3x. So here's 3 x's, here's 2 x's, that's 5 x's. And inside here, this is 2 by 3, 2 times 3 is 6. We have x squared plus 5x plus 6. We could expand that out for this one. We could do x plus 5. And we could do x, well, x squared would be hard, but we could do x squared plus 2x minus 3. And it would all work out the same. Every piece would have to get multiplied by every other piece. Okay. So we do that here. X times x is x squared. X times 5 is 5x. We're done distributing this x. Now we start with 5. 5 times x is 5x. And 5 times 5 is 25. So just like Brandon said, it's the distributive property. We're not restricted to just FOIL. X squared plus 10x, 25 minus 2, 23. X squared plus 10x plus 23. This is vertex form. This now is called standard form. Standard form is when we have f of x equals ax squared plus bx plus c. A is always with x squared, b is always with x, and c is always the constant. A is the coefficient of x squared, b is the coefficient of x, and c is the constant. So we go back to vertex form. If it's written in vertex form, we can find the vertex, we can find other points, and we can graph it. As simple as something like that can be to graph. If we're here, though, it's not as easy, but there are some things, some patterns that we can pull out of it. Okay. The first thing is that line of symmetry. that line that goes right through the parabola, cuts it directly in half. Okay, it goes right through the vertex. It's that mirror that the right side can be reflected over to get the left side, vice versa. We can find it as x equals negative b, this b right here, over 2a, 2 times this a right here. Negative b over 2a. It's not as easy as just saying the vertex for this one is -5, -2, but it is something. It is a starting point. So, just as an example, if we look at 4.1 again, to 4.1 number 23. We can find that line of symmetry. X equals negative b over 2a. What's b here? What's b in the standard form equation? What? It is 8. You find your x squared, your x, and your constant. X squared always has a, x always has b, and c is always a constant by itself. So b is 8, so negative 8 is negative 8. 2 times what's a? Negative 4. The number in front of x squared is a. So we have negative 8 over negative 8, so 1. So the line of symmetry is that x equals 1. So x equals 1, there's our line of symmetry, cuts right down through the middle of the parabola. Well, if this line of symmetry cuts the parabola right in half, then what's that point that it goes through on the parabola? It goes right through that vertex. Well, so far all we know is where it is, like horizontally. That's where the vertex is. It's somewhere here. But is it up here? Is it here? Is it down here? Is it down here? How do we know? How can we find out?
Plus 2 in the equation. So
It's got an equation.
well, it's got the equation at the end of the equation has the plus 2, like the previous one we're working with.
Okay.
Safety, so
It is not safe to assume that. Okay. That's not necessarily going to be true. In fact, I would say it would be safe to say. Well, I don't know if it'd be safe to say that that would never be true, but it won't. It's not a good rule of thumb at all. Yeah.
Can you see the homework?
What we know about the vertex is that it has an x value of 1. How do we find the y value? How do you find the y value if you have the x value?
plug x into
You plug in x and it gives you y. That's exactly what this equation does. It's what this function is made to do. It takes x's and turns them into y. So y is equal to -4 times 1 squared plus 8 times 1 plus 2. I'm going to have from right here. We know the x part of the vertex is 1. -4 times 1 plus 8 times 1 plus 2. That would be 10 minus 4 is 6. Y is 6. Comma 6. That's not enough. We need more points. How can we find more points that we can draw our graph through? You can plug in some more numbers for sure. That's probably the best way that we can come up with. What's a number that'd be really easy? Like we're going to plug in an x value, right? What's a really simple x value to plug into this equation over here? 0, 2 wouldn't be bad, and 2 would be a good choice because it's right here, right? This x value is 2. But look at this. If we do plug in 0, and we figure out what that y value is, then we get 2 for free, right? Because it's symmetrical. So we can just reflect it over to 2, and well, the work for plugging in 0 is less. We put it 0, that's 0 times -4, 0, 0 times negative 0. So we just get 2, 0, 2. And since it's symmetrical, and this is 1 to the left of the line of symmetry, 1 to the right of symmetry, 1 to the right of the line of symmetry should also be at 2. Now we've got our vertex, got our line of symmetry, got those points help us to determine the steepness of the graph, and it's all working out. So we have standard form. We want to find a line of symmetry at x equals negative b over 2a. And we want to plug that in. We plug that in for x into the function, and that's going to give us y. That's going to give us the vertex, x comma y. This is x, this is y, that's the vertex. And plot a couple more points. You can really just plot one more point where it's really easy to plug in the x value, especially if you can plug in the x value of 0. If the vertex is right at 0, then plugging in 0 again is not going to be very helpful. It's just going to give you the vertex again. But if you can't plug in 0, that's helpful, and then you get the other side of the line of symmetry for free. One more form of a quadratic equation to talk about, and that's the intercept form. Okay? And it's called intercept form because it has to do with the x intercepts. What's an x intercept? The graph has an x intercept where?
It's where the line or curve or what have you intersects the x-axis.
Exactly. Okay. So we have this parabola shape, this curvy shape. Right? It either opens up, both of them go up, or both of them go down. How many x-intercepts could this shape have? 2. Could have 2. Any other numbers? Any other number of x-intercepts?
1.
1, it could. Just touches it. Right. Any others?
0.
0. It could have 0, 1, or 2. How could it have 0 x-intercepts?
It's negative and it has a vertex lower than x.
Okay, so it's upside down and its vertex is below the x-axis. How could it have 1?
0, 0.
Okay, there's an example. It goes right through 0, 0. It could also go right through here or right through here and just touch it and go. And how could it have 2? Upside down. Touching the x. Fine. At 2 places like this. Right. 1 right there and another one right there. That's 2 x-intercepts, 1 x-intercept, and no x-intercepts. What do all these x-intercepts have in common? What are the coordinates of all those x-intercepts have in common?
Y is 0.
Y is always 0. 0, 0, 0. 0, 0, maybe 5, 0, maybe 9, 0. But they're all going to have an x-intercept of 0. Right? Or a y value of 0. Y equals 0. Well, that's what all these functions do. They say y equals, right? Y equals the stuff that you get when you plug in x. Okay? So the x-intercept is what you is whatever x value it takes to plug in and get 0 for y. Okay? So what if it was written like this? Well, if we multiply these together, we'll certainly get an x squared, an x term, and a constant. You can multiply those together and verify that yourself. But if we don't, and we leave it like this, then it's pretty convenient because if we want to find our x-intercepts, all we have to do is plug a number into here that gives us a y of 0, right? We plug a number in here, we do all the math, and what? Y is the result, right? So what can we plug in for x that will give 0 for this whole thing? What ideas do you have? What number can you plug in for x here? And once you get this number, and you get this number, you multiply them together, you get 0. Or just throw a number out there. Just throw it out, take a wild guess. 4. Okay, let's see what happens when we plug in 4. 4 plus 3 times 4 minus 5. 4 plus 3 is 7. 4 minus 5 is negative 1. So we got negative 7. So that didn't work out. But maybe just seeing me plug it in and then get two numbers and multiply two numbers together might give you an idea.
Negative 3.
Negative 3. Negative 3 plus 3. Negative 3 minus 5. Negative 3 plus 3 is 0. This is negative 8, but that doesn't really matter because what's going to happen when you multiply a number by 0?
0.
It's 0. Okay, so x equals negative 3. That works. And what? Plus 5. Positive 5. Yeah, this will give us 0. 5 minus 5 is 0. This will give us 8. But that doesn't really matter, right? That's 0 times 8 is still going to be 0. So if we plug in 5, we'll get 0 for y. We'll get another x-intercept. Any other numbers are going to work? Nope. Maybe you think there's a different, like I can maybe multiply it out and then rewrite it in a different way with two different parentheses? You can't. This is the only way. So, only negative 3 and only 5. Only if this equals 0, right? Or if this equals 0. If this equals 0, you have 0 times something is 0. If this equals 0, you have 0 times something equals 0. Right? And if we just solve these equations, x equals negative 3, x equals 5, right? We subtract 3 from both sides, add 5 to both sides, and we get to 2x values. If we're just multiplying two parentheses together, we're not adding things or subtracting things afterwards, then it's just the product of two numbers. The only way to multiply two numbers to get 0 is to one of them to be 0. You have to multiply by 0 to get 0. Okay. So for this one, we have found two x-intercepts. One at negative 3, one at 5. And all parabolas have, what's special about the shape of a parabola? It's nice. And what?
Round.
It's round. It's round in a specific way. It's round in such a way that one side is symmetrical, right? A reflection of the other side. So if that's true, then these two things must be on either side of some line of symmetry, right? Where is that line of symmetry? Huh? It's y. The y line. Oh, right here? You think it's right there?
No, it's in the middle. Sorry.
Middle of what? The middle of the 2 points. Exactly. Where is the middle of those 2 points? How do you find it right in the middle of any 2 points? Of any two numbers? What? Add and divide by 2. You find the average of the two numbers, right? 5 plus negative 3, or 5 minus 3 over 2. 5 minus 3 is 2, divided by 2 is 1. So this must be the line of symmetry. And what will you find in the line of symmetry?
The vertex.
The vertex. You'll find the vertex on the line of symmetry. So now we have x is 1. We can plug 1 into here. We have 4 times negative 4, negative 16. Negative 16 is where we'll find the vertex, way down here, negative 16. And then we connect our points and we have a parabola again. So vertex form, probably the best. Find the vertex, find a couple of points, it's done, it's really easy. Maybe intercept form is next. You just say, well, whatever turns this into 0, negative 3 in this case, and whatever turns this into 0, those are my two x-intercepts. Right? And then right in the middle I find my axis of symmetry. And then standard form probably at least good, right? Standard form, we're having to do negative b over 2a, and then take that number and plug it in for x, and then find the y value, that's the vertex, and then once we finally found that vertex again, we can find another couple of points and draw our graph.
Wait,
What?
I wanna break those steps
Okay.
down.
If you're doing that while you're.
And if it says,
Trying to pay attention.
again, if it says, take this equation, maybe it's in vertex form or intercept form, write it in standard form, it just means multiply those parentheses together, right? This will be the last time I say this word FOIL then. Okay? Now I'm done saying that word, I'll never say that again unless I make fun of it.
Wait, what?
Mock it. FOIL.
You said it again. You sucked it.
Now you have to have a joke.
Mark this.